Welcome all of you to this module. I will be covering regression models. So, the first part would be linear regression for multiple variables, and then this will be followed by logistic regression. So, this is a pretty old topic in the area of statistics and is considered as a tool in supervised learning, and the roots to linear regression stem from the work of Gauss, who used the idea of least squares for a linear fit. Let us consider the following motivating examples. Suppose I am given the body mass index and I have a list of these body mass indices for individuals, and I am interested in predicting the lifetime of an individual. Imagine an example in agriculture. Suppose I want to predict the crop yield and I am given various parameters such as soil pH level, moisture, ambient temperature, etc. Can I come up with a model for predicting crop yield? How about another example in predicting sales given an advertising budget? We may have advertising in radio, advertising over television, over newspapers, maybe social media. So, if we bring in all these parametrics, can we predict sales given our investment in the advertising budget over various media sources? So, these are common problems that we encounter in statistics, and since we are dealing with machine learning and neural networks essentially, which is a subtopic within machine learning, we must understand some basic ideas behind regression to proceed forward. Now, we are interested in predicting the quantitative response of a variable y given the variables x1, x2, so on till xn, right. For example, in the crop yield question, x1 was maybe the soil pH level, x2 might have been the moisture content, so on and so forth. So, we can have different variables and we are interested in predicting the quantitative response of a particular quantity. This can be scalar, in some cases we can also formulate a vector kind of formulation. We will assume scalar for this moment. So, what do we seek within these models? First, we seek relationship between a variable to a quantitative response. This is very important. We seek relationship between a variable to a quantitative response. Second, we may want to assay the strength of the relationship and which variables are statistically more significant, right. This is very important. For example, if you think about the advertising situation, maybe we can think about more sales probably with newspaper advertising versus possibly over the television, because there are more people that read the newspapers, etc. So, we may need indicators which assay the strength of the quantitative response, and we would like to accurately predict the future. This is very important, and there are other motivations for this problem. Let us consider a simple linear regression problem which is over a one variable case. Y is approximately alpha naught plus alpha 1 x. So, this is the kind of relationship that we want to formulate using the model, that is we are regressing y on x. Alpha naught is the intercept here, alpha 1 is the slope. So, this is basically a linear relationship, and we need to estimate these parameters alpha naught and alpha 1 from data. At this point, you will ponder that these are just approximations. That is the reason why we have written an approximation sign here. Y is approximately equal to alpha naught plus alpha 1 x. In the true case, we do not know how the relationship is, right. We want to keep the model simple and we want it to be a linear model. So, therefore, we are expressing it in this form. And you should also observe that data could be possibly noisy. So, we will handle this subsequently. Now, how do we estimate the coefficients, right? All I have is the data which comprises of the pairs xi yi for I equals 1 to n. I have n data points, and alpha naught hat and alpha 1 hat are estimates of the model. They are of the model parameters, right? They are estimates of the model parameters. Now, to predict the future response y hat in response to variable x, we formulate y hat to be alpha naught hat plus alpha 1 hat times x. So, this is our predictor, and using this predictor we need to kind of minimize in some sense the deviation of what you observe in yi with respect to your prediction, which is yi hat according to this model. Now, in order to go one step forward, we formulate the error for the data point xi yi with respect to the predictor yi hat, right. I am given data points xi yi, for every xi I have yi, and I formulate this predictor yi hat which is according to this linear relationship. Now, epsilon I, which is yi minus yi hat, can be simplified as follows. So, this yi hat we will replace it with this quantity alpha naught hat plus alpha 1 hat times xi. So, this is my deviation. Or I would say error. Now, how do we fit the model parameters? To fit the model parameters, we need to formulate a criterion for the error. One of the popular choices would be the least squares criterion. What we do is we consider the residual sum of squares. So, I have these epsilon i's for I equals 1 to n. I basically take the squared error and I sum these over all these square errors. You may at this junction kind of wonder why this square error, why not the cube error or error power 4 or absolute error, so on and so forth. We like to do quadratic optimization because we get a unique solution and it is easier for us to deal with the mathematics. So, therefore, considering these options, we like to stick to quadratic optimization. But bear in mind one can also have the ML estimate etc., provided we know some parametric model on the data. Now, I formulate the residual square sum according to this equation. Basically, I plug in yi hat and I replace it here. Now, the goal is to minimize this residual square sum over the parameters alpha naught hat and alpha 1 hat. So, the procedure is straightforward. We invoke basic calculus. I take the derivative of RSS with respect to alpha naught hat and alpha 1 hat, set that equal to 0, and I verify that the second derivative with respect to these variables are positive, so that indeed we are minimizing this. Okay. Now, once we formulate this, it is easy for us. We take the derivatives and set it equal to 0. taking the partial derivative of RSS with respect to alpha naught hat, we will end up with this equation here, which is minus, because you have a square there and there is a negative sign sticking to sticking before alpha naught hat. So, therefore, we have a minus 2 summation I equals 1 to n within braces yi minus alpha naught hat minus alpha 1 hat xi, and this has to be equal to 0. So, you pull the negative 2 there, what we will end up with is this equation summation I equals 1 to n yi equals, so you have the sigma I equals 1 to n alpha naught, after transposing this negative becomes positive. So, this is n times alpha naught hat plus alpha 1 hat times summation I equals 1 to n xi. This is straightforward transposing this equation, so that we have positive quantities on both sides of the equation in terms of the sign. Now, we define x bar and y bar to be the sample means, and x bar is just 1 over n summation I equals 1 to n xi, and y bar is 1 over n summation I equals 1 to n yi. So, using the simplification, we get alpha naught hat is y bar minus alpha 1 hat x bar. So, from equation A we can simplify to computing alpha naught and alpha 1 alpha naught hat and alpha 1 hat given the sample means x bar and y bar, and this gives us equation B. Okay. Now, once we understand the trick, we do the same thing with respect to alpha 1 hat. We take the partial derivative with respect to alpha 1 hat. So, you have the square term, so therefore, you have a 2 there, and since you have a negative sign sticking in front of alpha 1 hat, so you have a minus sign there, and then the partial derivative of this term alpha 1 hat xi is xi, that is when you take the partial derivative with respect to alpha 1 hat you will end up with xi. So, this is what it simplifies to. Now, you rearrange this equation slightly, this minus 2 will be pulled out. So, therefore, we get summation I equals 1 to n xi yi is alpha naught hat summation I equals 1 to n xi, because you group this term with this here, and again you have this term grouping them, and then you have this, right. So, you have xi yi in one case, you have alpha naught sticking out xi summation I equals 1 to n, then we have alpha 1 hat summation I equals 1 to n xi square. Now, using the previous relation that we had, which is this equation B into this equation C, we can do further simplification. So, let us focus on this alpha naught. This alpha naught can be written as y bar minus alpha 1 hat x bar, right. And now, we simplify this further, it looks a little messy. So, what we will do is we will group alpha 1 hat and then the rest of the terms that do not involve alpha 1 hat, right. After doing a little bit of algebra and simplification, we will end up with this equation. This does not look very intuitive, or at least it is not easy for us to remember this. There is not much of a symmetry that you can see in the numerator and the denominator. So, let us try to simplify the numerator and the denominator in terms of a compact form. We make the following observations. These are sort of straightforward. Y bar times summation I equals 1 to n xi is n times y bar times x bar, because you multiply and divide by n in the left hand side of this equation, right. If you multiply by n and divide by n, so you have n times y bar, and this quantity is essentially your x bar, right. Similarly, you can do this for x bar times summation I equals 1 to n yi, and you will end up with n times y bar times x bar. So, same trick, n here, 1 over n here, and this is y bar. And if you take summation I equals 1 to n x bar y bar, because there is no indexing here, it is n times y bar x bar, there are n terms here, right. All of these quantities are essentially the same. Now, using this from these observations, which I denote by equation 1, we simplify the numerator in this equation d that I wrote here. So, this is what I have. So, I basically add and subtract these n times x bar y bar terms in a way that I can simplify. So, observe this. So, this is the numerator term from d. Now, you can simplify using this, because there is a negative y bar summation I equals 1 to n xi. So, I add so basically I add summation I equals 1 to n x bar y bar, and I subtract x bar times summation I equals 1 to n yi. So, this is exactly what I have in the numerator, but if you simplify what I have on the right hand side, if I look at this equation here that I will indicate in green, right. If I simplify this messy looking equation involving all these sums, it can nicely simplify in this form: summation I equals 1 to n xi minus x bar times yi minus y bar. This is a very compact form, and all you have to do is basically compute the sample means, subtract it with respect to each of these xi's and yi's, and take the product and sum them over all the data points. Now, the denominator can also be simplified similarly. So, let us consider the denominator term, which is summation I equals 1 to n xi square minus x bar times summation I equals 1 to n xi. So, this can be written in compact form as summation I equals 1 to n xi square. So, now the same trick like what we did earlier, an n sticking here, a 1 upon n sticking here. So, realize this as x bar. So, therefore, you have summation I equals 1 to n xi square, first term is kept the way it is. The second term simplifies to n times x bar, which is n times x bar square. Now, this is not enough. What we do is we add and subtract n x bar square, right. So, we will do the simplification. So, this is summation I equals 1 to n xi square. Now, this n x bar square is written like this, and I remove minus 2 times x bar times summation I equals 1 to n xi, and this simplifies as 2n times x bar square, the same trick, right. Take an n here and a 1 upon n here, and this basically gives us this result, and this is in a nice a minus b square form, and if we simplify this we get summation I equals 1 to n xi minus x bar square. So, this is a compact form. Now, if we write it in a simplified form, alpha 1 hat is given by this equation. So, this is easier for us to remember, because all I have to do is subtract the sample mean from xi, sample mean from yi, take the product and take the sum, and in the denominator I just have to subtract the sample mean from xi, and then I just have to compute the square sum. Okay. So, this is an easy way to remember. Now, having done this, we ponder if this idea is easy to generalize for the multivariable case. Answer is not, because we will have to solve a lot of simultaneous equations involving all these sums, and it becomes pretty messy, and we will look into the problem as we go further down the investigation. But before then, let us consider this regression problem with observation noise. Okay. Here is the setup of the problem. Typically, we may not know the true relationship of x with y, and let us assume that y is some f of x, and there is a random term epsilon here, which typically indicates noise. And one of the important assumptions is we can assume that the noise is independent of x and is 0 mean. Typically, you may not get 0 mean. If it is not 0 mean, you can always make the mean 0, you can get the bias to 0. Now, let us try to assess the accuracy of the fit, and we may need some simplifications under this purview. Right. Another important practical situation is that the errors epsilon I need not be correlated. So, they will have to be taken into account appropriately, but for our simplifications we assume that epsilon is independent of x and has 0 mean. So, we stick with this assumption. Because if it is correlated, we can decorrelate it. If it has non-zero mean, we can always get it to 0 mean. So, we can take care of these things. Now, let us simplify this problem. We want expected value of y minus y hat square. Y is basically f of x plus epsilon, this is where we started off, and f hat is some function that we have to approximate. We do not know, we have to assume some model, for f hat. F is the true model, f hat is what we need to assume. Let us simplify this further. We group the terms. So, we have f of x minus f x hat plus epsilon. So, you do the a minus b, a plus b square here, right, where a is f of x minus f hat of x and b is epsilon. So, I am doing this a plus b square. You simplify, you have expectation of f of x minus f hat of x square. Since expectation is linear, right, you have 3 terms. You have one term which is f of x minus f hat of x square, then you have epsilon square, and then you have f of x minus f hat of x times epsilon, and expectation is linear, and since we assume that the error is statistically independent of x, we can take the expectation into this product, and simplifying using this 0 mean assumption for the error, this term drives to 0, right, this is 0. So, all we are left is the expectation of f of x minus f hat of x square plus the variance of epsilon. Because this is 0 mean, the second moment happens to be the variance. Now, we cannot reduce the variance of epsilon. This is observation noise. I mean, we can remove the correlations etc., and we can simplify some things, but beyond which we cannot further simplify. We live with this error. But depending on the choice of f hat, because f hat is our model, it is our choice, we can minimize this quantity, which is we can minimize this expectation of f of x minus f hat of x square. So, in the noiseless case, y is f of x, and we assume the model f hat of x to be alpha naught plus alpha 1 x. Maybe I can put estimates here, right, if I want to figure out what the estimates are. So, I can choose my model appropriately that can reduce the error. So, if I choose higher terms in terms of my modeling, I choose alpha naught plus alpha 1 x plus alpha 2 x square dot dot dot, I can simplify this further, right. I can get a better fit, but the second term, which is variance of epsilon, I cannot reduce this further. I think this is an important note when you have to deal with things in practice.